Hello everyone, welcome to topic 6.7, Bond Enthalpies. By the end of this, you should be able to calculate the enthalpy change of a reaction based on the average bond energies of bonds broken and formed in the reaction. So remember back when we were drawing the chemical structures, the Lewis structures? That's coming back, and we got to use it for this. So let's get to it. In a chemical reaction, the bonds in the reactants must be broken and remade into the products. Breaking bonds always requires energy, while making bonds always releases energy. I'm going to start sounding like a broken record, but please make sure you are paying attention to that. You can estimate the potential energy change for a reaction by adding up the bond energies for breaking all the bonds of the reactants, and then adding up all the bond energies for making all the bonds in the products. If the energy required for breaking bonds is greater than the energy released in making them, you have an endothermic process, and then the vice versa is true. If the making is greater than the forming, then you have an exothermic process. Okay, so there are known values for these. You would be given these on a test. Okay, so they would give you a table with these listed already. You don't have to memorize them. So in summary, the equation for this is the sum of the energies, which are here. This is all of our delta H values, broken minus all of those formed. And the reason you have to draw it out is for every CH bond there is in a compound, or on the reactant side total, you have to multiply it by that quantity. And if there is a coefficient in the reactant, you have to multiply that by the coefficient. So we are going to look at it because it's total number of that bond stoichiometrically. So that is why you must always draw that molecule so you can determine the number of bonds and the order and number of type of each bond. So double, triple, single, and then how many of each kind you have. A way to remember how to calculate the overall reaction energy, because it's a little weird, is using the mnemonic basketball is my best friend. Maybe not your best friend, but hey, bonds broken minus bonds formed. So that way the F follows the mnemonic. Okay? And oddly enough, this ends up being your reactants minus products, which is technically backwards from what we traditionally approach this as, which is why you need to figure out the mnemonic, or remember it's always the broken minus the formed. Okay, because formed is an exothermic process, so you need that negative sign. Okay, so looking at this, we are going to go over the IDs using these concepts and look at some practice problems. Okay, so how much heat is released through the complete combustion of propane? So your first step is not draw them out yet. You need to balance the reaction. So take a minute, pause the video, and please balance this reaction. Okay, so through this you should get 5, 3, and 4 here, and checking it, we have 3 carbon, 8 hydrogen, and then 6 plus 4 is 10 oxygen. Okay, so first balance, then 2 is draw if it's not already drawn for you. So for propane, we have 3 carbons in a row, and then 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Then drawing oxygen, you have this, and then carbon dioxide, and finally water. Your next step is to identify the bonds. So ID bonds and your number of each. So on the reactant side, we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 8 C to H bonds. We also have 1, 2 C to C bonds. We don't need to multiply them by a coefficient because there is no coefficient here. However, on the other side, we see we have in the molecule 1 double O bond, O double O, but we have 5 of those, so we would multiply that by 5. So I have a total of 5 on the reactant side. We're going to repeat this process on the other side. So we have the C double bond O, and there's 2 in the molecule, but I have 3 of those molecules. So 2 times 3 is 6 total. Then looking on the other molecule, we have H bonded to O, and there's 2 there, but we have 4 of those molecules. So 2 times 4 is 8 total. Okay, so these are my bonds being broken, and these are my bonds being formed. Because you form them in the products, you break them in the reactants. So I can take these values and I can do 8 times the bond energy for CH, and we would look that up on this table, which is 413. And we repeat this process. 2 times the bond energy for carbon, which is 348. And then 5 times the bond energy for oxygen. And you need to make sure it's the double bond O and not single bond. And it might be listed as O2 because that is the molecule. And it's that. So we would then multiply all of these, or multiply these across and then add them all up. And you should get 6,475 kilojoules per mole. And this is bonds broken. So let's look at our bonds formed. Okay, I'm going to actually take that part off. So 6 times the bond energy for carbon dioxide, or C double bond O, is 799. And then 8 times the bond energy for the OH bond is 463. So then we're going to do the same thing and add them here, and you should get 8,498 kilojoules per mole. Okay. So since the delta H is equal to, for our reaction, delta H of the reaction is equal to bonds broken minus the bonds formed, we can subtract these two and get our final answer. And when you do that, you should get negative 2,023 kilojoules per mole. And that is just ironic that it is for this school year that I'm recording this, and it's 2023. But this is our final answer. Okay, so remember, bonds broken minus bonds formed gives us our final energy. So let's practice that with this one. So our first step is to check that if it's balanced, and if we check, we see 1 carbon on both sides, 2 hydrogen, 2 chlorine, and 2 bromine, so it is balanced. So your next step is to draw it out. And so drawing it out, you should get and then valence electrons around here. And then bromine is Br to Br with valence electrons. And there's not a lot of room on this one. So we need to determine if it's endothermic, exothermic, and calculate the energy involved. Well, you need to calculate the energy to figure out if it's endo or exothermic. So here we go. Okay, so we have our compounds. So I want you to first identify which bonds are being broken, and then we'll check in, and then we will do bonds formed, and then we will do the mass. So first identify which bonds are being broken. Okay, so you should have seen that you break the CH bond on the reactant side, the CCl bond on the reactant side, and the Br to Br bond on the reactant side, but that you have 2 CHs and 2 Cls. So next you want to do the bonds formed. Okay, so identify which bonds are being formed and check back in. So pause the video and do that now. Okay, so from this you should see that you form 2 CH bonds, 2 CBr bonds, and 2 Cl to Cl bonds. So now your next step, if we're remembering, is to determine the amount of energy associated with that. So you are going to look up the energies on that table, put them in here, multiply them together, and add them up to get the energy associated with breaking bonds, and repeat that process with the energy associated with forming bonds. Okay, then resume the video after you have done all of that to check in to figure out if you found the correct energy for bonds broken and formed. So please pause the video and do that now. Okay, and so for bonds broken, you should have gotten 1,675 kilojoules per mole, and bonds formed is 1,620 kilojoules per mole. Now, remembering back, the delta H of the reaction is equal to the bonds broken minus the bonds formed. So that is our next step, where we take the energy associated with breaking bonds, and we're going to subtract the energy associated with making bonds, or forming them, to get our final answer, which should be positive 55 kilojoules per mole. Okay, and so from this, because it is positive, we know that the reaction therefore is endothermic, because it is absorbing energy and our delta H is positive. So using these as examples, complete the practice problems that are below, check your work either as you go or at the end, and thank you guys for tuning in.